amount of if you just look at the amount of observed grid cell at each particular time point, that you can say that is being presented over here. So the this is the data product, and we just identified, for example, in January 1850, what is the percentage of percentage of grid cells which were being observed. So in total, it was 5-degree grid cell. So in total, these are 2592 grid cells, and out of those grid cells, for example, roughly greater than 10% were observed in January 1850. And similarly, this situation goes up slightly, then goes down, then goes down. But as in the recent years, for example, 2000 and above, these are more well observed, because more stations are being installed, and more observations are there. So more grid cells are observed in the recent years as we are moving towards in 2000 and on. Now, in terms of time as well, for example, in a particular grid cell, what is the percentage of time, and not the count of time that is being observed, and that count is just being presented over here. So this is a huge scale, but anyhow, 0 means that this is a very small number of time which are being observed for that particular grid cell. And then as you move towards the red section, we are moving towards the more well observed grid cell in terms of time. So you can see, I mean, these are red, so these are well observed. I mean, more times are there for these grid cells, and similarly, but in polar regions, the situation is very bad in terms of time as well. I mean, this is why it's so very few observations are there probably. Now, what is the consequence of that? For example, there's a report which is IPCC ER5, so Intergovernmental Panel on Climate Change, and this has been taken from the 5th assessment report because it was based on HATRO4, but obviously the reports are constantly evolving. However, if you need to identify, if you just look at this figure, it means that within this particular time duration, and using this particular data, because I was working on this data, so I was bound to use this particular plot. Otherwise, again, the new reports and the new version is there. Anyhow, so there's a lot of white space, which means that again, we are unable to. I mean, they were unable to compute the trend estimates, a reliable trend estimate in a relatively recent time period, that is 1901 to 2012. Because they do not have enough observation for that particular grid cell in terms of time to compute the trend. So whatever is white, it means they do not have enough grid cells to compute the trend. And whatever is colored, I mean, they are able to, there's a sufficient amount of observations to create or to compute that trend. So this plus sign means that the regional trend estimates are significant, and where there is no, I mean, plus sign, the trend estimates are insignificant. So that is being presented over here. Again, if we just need to know what's going on in this part of the world, and we need to identify the trend, and we need to create this type of a map, we need to know what the full temperature estimates are throughout the world. Now, I mean, it's not like, I mean, this particular feature has not been picked up by other people. I mean, this is a very common problem, and it was being picked up differently by different groups. For example, for UK Met Office and HATRO4, they do not do any kind of spatial interpolation. However, for more recent version, which is HATRO4, they have provided 2 versions. One is spatially interpolated, and the other one is without interpolation. So, and now the situation is different. But this for HATRO4, it was without interpolation. Then NASA, they are using linear inverse distance weighting for a very long time, but now they have improved their interpolation scheme, and that is more rigorous based on spatial covariance structure. So they are moving towards improving it. However, they're successfully, I mean, doing it using this as well. Then this is being provided by NOAA, and they use linear spatial interpolation. But again, they do not go beyond a certain range, because I think probably the estimates would not be very reliable. And so they're just going beyond a certain range. And again, there you can see that there are certain gray areas. For Japanese group, I mean, they use optimum interpolation, which is ordinary kriging again. But again, there are gray areas, as you can see over here. And for best, they use Gaussian process regression, but gray areas are there as well. So it's not fully dense if we just look at these this picture from different groups as well. Now, this is the point that we statisticians can intervene and help with spatial interpolation. And this is what we, as a group, attempted to, solve this interesting problem. So what the spatial model is, so like any linear model, we have got the observations and there is a spatial process. So we are trying to model these observations in terms of the spatial process, and then there's an error term associated with that. And this is Gaussian random process, and it has got some which is based on some covariance function, and that covariance function has got some covariance parameters which are just being dumped over here. So this is a vector of maybe, for example, for Mitterrand, it would be range and a cell and maybe a smoothness parameter, and this is the error term, and this is the measurement error variance, which is called nugget variance in this particular case in spatial model vocabulary. Now, multi-resolution lattice kriging is very much similar to the standard spatial model. Means we have got observations, the spatial process, and the error. So again, we have got the observations, we have got the spatial process, and then the error term. The only difference that it creates, that it models the spatial process as a sum of many processes. For example, there's the first process G1x, G2x, and up to so on GLX. And typically these spatial processes are just being defined in terms of different resolution levels. So for example, for the first process, this particular process is a linear combination of the basis functions. And basis function is just the extra information that we are feeding in to understand what's going on in the spatial process. So these are fixed, whereas the coefficients of these basis functions, these are random. And the basis functions are radial basis functions, which are zero beyond a certain range. And these are random, and these are modeled as Gaussian Markov random field. So it happens in a way that this entire process is just being considered, for example, as a sum of many processes, and each of the process is based on different basis functions, and those basis functions are defined at different resolution levels. For example, the most sparse one can be at 5 degrees, then the other one could be at 2 degrees, and then at 1 degree. So this actually, the basis functions are just being organized at different resolution levels to understand what's going on, to capture the variation at each level. The multi-resolution lattice kriging, which is being provided by Nishka and the colleagues, that is actually based on likelihood-based inference, and they use profile maximum likelihood approach to estimate the covariance parameters. We can use this. There was no harm in using their technique and their inference methodology, but the problem is that the kind of data that I was handling was very large, and again, likelihood requires typically the inversion of the covariance matrices, which are typically large in case of large observations, and again, that requires some suitable a technique which can aid to just fast track things. So we proposed an alternate inference methodology for multi-resolution lattice kriging. So apart from the ML-based or likelihood-based inference, we can go for not exact but approximate Bayesian approach, and that was based on the variogram, and variogram was being used as a summary statistic in this case. Now, what is a variogram? A variogram is just like, we have got a simple variance that we try to explain in the univariate analysis, a covariance matrix that we try to explain in a multivariate analysis, and here in spatial statistics, we try to explain the covariance structure among the observations, which is the covariance. The covariance function is actually this one, which is sometimes called the variogram as well. Covariance function is it is slightly different. Because it goes this way if we just go for the covariance function, but broadly we can just group them in one thing. Anyhow, so what are the features of this covariance structure that is being presented by the variogram is that there's variation in the observations, and that variation varies if you are just increasing the distance. So we are increasing the distance, and the variation we can see over here, and after a certain distance, the things neutralize, so they do not change much; they're just flat. So the point at which the distributions are unrelated to each other, or they did not vary much, that particular threshold is called the range parameter of the variogram. And that is the error variance. I mean, the point it is just hitting the y-axis, not exactly hit, but it is very close to that. And the total variance of the spatial process is called the SIL, and this from nugget to this end where it just neutralizes and do not very much, that part is called the SIL. So this is the total variance, that is the SIL. So anyhow, I use this classical estimate theoretical variogram, in fact the empirical variogram, to just propose a new algorithm to estimate the parameters of multi-resolution lattice gradient. But before that, let's have a look what ABC is. So firstly, the main problem that creates likelihood for large data settings is likelihood function. So ABC is a likelihood-free approach. We do not have to evaluate it if we just get along with that. So it is a likelihood-free method, and that gives you an approximate posterior distribution of the parameters given the data. That is the target of the classic Bayesian inference, and it is a very viable approach. So we do not need to evaluate the likelihood, and typically it works well in the situations where the data is very sensitive with the changing parameters, or it is easy to simulate the data that looks like the real data, because we need to compare it ultimately. So the basic idea is we simulate from the model for a given set of parameters. These are typically the priors. And then we run many simulations for many parameters. And then we compare the observed data and the simulated data. And we retain those parameters where the simulated data is close to the observed data. So we simulate the data with certain parameters. And if that matches with the observed data, we are happy with the parameter, and we just treat that as particular as a sample from the posterior distribution. And if it is not close to the observed data, then we are unhappy, and we just drop it and go and just simulate another parameter and simulate the data and check whether it is close to the observed data or not. So that's very simple. Now, how does it work? So this is a spatial process. It means, we have got the covariance parameters, we have got the nugget variance, and the target is we try to estimate, we try to estimate the posterior density of the parameters and the nugget variance given the data, and that requires the likelihood and the prior distribution. Again, this is if we just need to run. It's hard that we do not need to evaluate this, although it is equivalent to that, but we'll try to sample directly from this particular posterior distribution using ABC. Anyhow, so we just check this method before implementing it over multi-resolution lattice tracking. And so we just tested it over the classical standard spatial model. And this is what the story is. So for example, this is for the SIL parameter, this is the nugget variance, and this is the range parameter. We have considered the log just to pull down the magnitude of the variation. Otherwise, it is just the same picture. So the gray thing over here is the prior distribution. And the solid black is the approximate posterior of this parameter, which is the SIL parameter. In this particular case, the green line is the true value of the parameter with which we simulated the true structure or of the observations, and the red is the exact posterior. Exact posterior is not the analytical one, that is based on NCMC. Similarly, as you can see, it's not that bad considering the amount of computational gain that we were getting from this. And again, it's not very bad. It is falling in the credible intervals, and the situation is not very bad over here as well. So we use this in multi-resolution lattice tracking, but this was for the standard spatial model. So again, by using approximate posteriors, like I said before, because it just bypasses the evaluation of the likelihood function, that is the inference methodology which has been used by Nishka and the colleagues in the standard methodology, and I worked with them and created an alternative inference methodology based on ABC. And the reason of doing that was because it is very easy to parallelize. So we can just run the bits of the code independently from each other, and that can save a lot of time, which is not possible if we are doing the likelihood evaluation. It is, but this is embarrassingly parallel. There are certain situations where we can parallelize the NCMC and other methods as well, but this is embarrassingly parallel. That is why we just picked it up. What happens? For multi-resolution lattice tracking, we just picked up the two parameters. There are others as well, but these are the ones which are going to affect the spatial predictions the most. So this is the nugget variance, and this is a sort of a range parameter. So it's like we simulated from them So it's like setting the prior, you can say. So we set a prior over these two parameters, and then we simulate it. We just draw one particular particle from here, one particle from here, and just substituted that and used a multi-resolution lattice Kriging model to simulate the data. So that synthetic data was being created. And over that synthetic data, we computed a some statistic, which is empirical semi-variogram. And that particular semi-variogram, which was coming from the synthetic data, was being compared with the original data set, which is the data. This is the observed data, and this is the semi-variogram of the variogram of the observed data. And simply by deviating them or creating a similarity matrix, we need to identify how good these particles were. And if the semi-variogram of the observed data and the synthetic data one are close to each other, means they are less than a particular threshold, that we typically decide that there are ways of doing it. So if it is less than a particular threshold, then we are happy with the particles, and we are going to retain those particles as part of the posterior distribution. And if they are not less than a particular threshold, then we need to go back, draw another particle, simulate the data, test whether it is close to the observed data, and again we need to check whether it is close. And if yes, we are going to retain it, and otherwise we are going to drop it. So this is a very basic classical rejection sampler that I used to create the temperature data product. Again, reason was that we need to gain the computation aspect, but there are more recent ones. I just implemented those methods over certain domains, but I do not use to create the temperature data product just due to the time. And those are, I guess, the more fancy, for example, sequential approaches, and they're based on important sampling. So those algorithms are fancier than these. Anyhow, so the temperature data product, to use this multi-resolution lattice Kriging that is based on ABC, so we can easily parallelize them. How does it work? So these are the temperature fields because I created two versions of these temperatures. So this was the previous version, this was the new one, and this is just the difference from the two. Anyhow, for example, how does it work? So this is a spatial field for again May 1861 that I showed you in the beginning, where there were a lot of gray areas. So anything that is purple over here, we know what's going on in those spots, and apart from these, purple spots, everything else was just gray. So now we know what's going on everywhere. For example, in Pakistan, I know what the temperature estimates are. In the polar regions, we know what the situation is. And there are some very nice patterns in the background that you can see. And these all make sense as well. There are ways of doing it. First of all, the graph should make sense. For example, if I just go back and show you the previous graph, for example, this one. So there's a pattern. Obviously, when the spatial interpolation works in terms of distance, so if there's a blue section over here, that would not make sense to me. So it has to be the average of the grid cells nearby. So it has to be some pattern of red or something, and that is what is being provided over here. For example, if I just so this blob particular is a pattern of red. So there is no blue in that particular bit. So that makes sense to me. The patterns are just picked up from the nearby stations which are observed, and that is the basic idea. We try to estimate what we do not know, considering what we know under certain situations in terms of the distance. So we know observations over here, and considering the covariance structure in these values, we have tried to just predict the estimates where we do not know anything. So now we know this is fully dense spatial field. Anyhow, so since we are making a prediction, so in a particular grid cell, we are making a prediction, or we are estimating what the temperature is at that particular location, for example. But again, there is an error associated with that. We are a statistician, so this field represents the errors, spatial interpolation errors, you can say, or prediction errors. What we have, considering the predictions that we have done in a particular grid cell. So those prediction errors are being presented over here. So there is as we expect, the closer we are to the observed grid cells, the smaller the prediction error would be. These are close to zero. And as we are just getting away from the observed grid cells, the prediction errors are large. So we know that we are more uncertain with, as we are moving away from the observed grid points. So that's that. That makes sense as well. So this was from the previous version, and this is just the difference between the two. So, I mean, this is from ABC. Now the situation is not easy. It's not like we have got just one spatial field for May 1861. It's not like that, I'll just implement that algorithm and I'll get just one field for this particular, for May 1861. For May 1861 in Hat-to-4 temperatures, there's not just one field for 1 month. There are 100 fields for 1 month, and situation is different in the recent version. So what do we mean by that? It means that, for example, this is beige and dark red, and this is now orange and red, and then these colors are changed in the north of Kazakhstan, as you can see. So it means that for this particular blob, for example, this darkest red, there's not just one observation that is there. There's a range of observations, and that range of observations has got some distribution, and that distribution is called the observational error in temperatures, which are being quantified by expert climate scientists, and they just provide and sample and then just give us this particular ensemble member. So it's not like this. I mean, we have got one field, we have got 100 fields for 1 month. So if we need to do that, it means we need to do spatial interpolation for these 100 months, and then we need to sample the errors in that as well. Anyhow, so what we did, we just considered, for example, the first temperature field, and I implemented that algorithm, which was ABC-based multi-resolution array splitting, to estimate the predictions and to estimate the errors in them. And then I used multivariate normal distribution to sample, to create a sample of, you can say, fields which are actually representing the interpolation errors in this particular field. So with corresponding to one ensemble member, there are 100 ensemble members corresponding to this. So this 100 times 100 is, you can say, this is a very large number. And since we were doing the parametric uncertainties as well, so one layer, the other layer, and then there's a layer of uncertainty errors as well. So this was a very large data set. So coverage errors plus the parametric errors were just being accounted for by ABC multi-resolution array splitting. Coverage errors, because we were doing the spatial interpolation and we were accounting for the, we were estimating the interpolation errors, and then we were sampling given those given those coverage errors, and we were drawing ensembles which are representing the coverage errors in them. And at the same time, we were quantifying the parametric uncertainties using ABC approach, because we were just creating the posterior distribution of the parameters, and those posteriors were just being folded in with quantifying the coverage errors. And since these two things were going on along with the observational error, which are being provided by these 100 ensemble members, and there they were, the earliest month that we have is 1850, and this is updated every month. So we have got a large data, huge data. So this is a lot of work. Anyhow, so in total, for example, if you just consider up to, I keep on updating that, but for example, I just considered this one, for example, for 1850 to 2018, we have got the recent ones as well. We have got 2028 months. And there are 100 Hat-to-4 ensemble members, so 2028 months, and then 100 Hat-to-4 ensemble members. And for example, if I just run a single job, it takes around 66 minutes to just process this, the algorithm that I just have discussed with you, to just run that. So it took 66 minutes. And that is also being done by just splitting the ensemble members in different groups and then running them parallel. This took this one. And in total, the parallel jobs which are being defined over one ensemble member, these are 20. And this multiplied by this is a large number, which is this number. So these are the total number of jobs that I need to just run to process it. And if I just multiply it with the one bit, which is 66 minutes, this turns out to be a very large number, and that is 61.97 months. So this is considering that ABC is easily parallelizable, considering that the code is being written in a very efficient form, but still it was not feasible. But interestingly, I mean, I just ran these jobs over UCL high performance computing, and interestingly, it was allowing me to run more than one job. So typically, when you just submitted 6 or 7 parallel jobs done simultaneously, so it took me 8 months of the work clock time to perform all these computations and to create this temperature data product. So that temperature data product is the results of those are being presented in the purple ones. So for example, there's a time series in the back. There's a previous version that I created, and that is being displayed over here. The difference between both of these is not much, because that difference is not much evident at a global scale. But if you just go at a regional scale, and if you just go deep in at a minute scale, for example, in terms of monthly time series, the difference is huge. So let's consider the purple one. So we have got a time series. So these are the annual averages, and there is an error associated with each annual mean. So that, in other words, the confidence intervals, the 95% confidence intervals. So these bands are representing the uncertainties, and that band is actually sampling the distribution, which is sampling, the observational. So this is just the fold of all these threes. The observational errors, which are being quantified by UK Met Office, and the parametric uncertainties, which are being quantified by ABC, and then multi-resolution error sprigging that was used to just identify the coverage errors, and those were then sampled. So these three are just being combined, and those errors are just being presented over here. So that was the summary of that. What I'm doing currently, because there's the huge impact of these errors at a regional scale. So I'm more interested in just identifying the impact of these at a regional scale. And initially, my temperature data product is based on Hetero 4, but there's a new version. So I'm exploring that as well, how it fits in with my research and other things. And these are the references. These are the temperature data products that I created, and this is the one I presented my work. That is based on ABC, and this was the previous one. These are the two temperature data products which are being provided by the UK Met Office, and this was the paper that I used, the spatial interpolation method that I used to propose the method and used to interpolate the temperatures. That's all from my side, and I'll be happy to take questions.
So the floor is now open to questions. I don't see any questions in the chat. So we can take questions, oral questions.
So maybe I can ask a question. It is fantastic, I must say. It's just it seems it's a lot of work. So where is it being applied? Is it, for example, in Pakistan? Is your research being applied in any real situation?
The unfortunate part of this is that the temperature data product is huge, and we need to do something to just pull it down and to make it usable for the general audience. But some of my students are working on it. They are creating the temperature data product out of it, so it is available. this version is available online, and it could be used. Anyone can use it, this temperature data product. But the ABC one is very large to handle, and we are just looking for a venue where we can just place it. For now, it is just sitting in my in my hard drive, or there in the UCL, a copy of it. So from there, it could directly be accessed, those who have got it. So we do not need to, but we are yeah, that's very interesting. In fact, we need to just delve back into it and identify a way to just shrink that data that still has the essence of the real data, maybe a sample of that somehow, so that we can just provide it for the general use of the people. But if anyone use it, I have got a copy of that to be provided on request.
Thank you.
Thank you so much for the interesting talk, Dr. Mariam. And thank you so much for coming to this webinar, especially at this hour of the day. So if there are no more questions, there are some thank you notes on our chat. So Professor Senija, she works in official statistics. She's from Croatia. She has sent her note of thanks to you. So thank you very much. Thank you again. So hope to see you around, and have a great rest of the week.
Thank you very much for having me. It was great meeting you all. Thank you. Thank you very much.
Thank you all for coming. Good night and good evening, wherever. Okay. Bye.
Bye.